field simulation of a Schwinger model, one small computer. And the field has kind of exploded in the recent, let's say, 5 years or so. And I invite you to have a look at more recent videos. This is by no means complete, but it's a start. So since we haven't talked about gauge theories in too much detail in this conference yet, I decided to give you an overview of the basic ingredients that all of these models have in common. And specifically, I will focus on the Hamiltonian formulation of gauge theories, which is somewhat non-standard in this field, but is of course much more well suited to do quantum simulations. So let's take a simple example that shows nevertheless the full complexity of the story. And that's what I will call a Z2 gauge theory of quarks and gluons in quotation marks in 2 plus 1 space-time dimensions. And how these theories are typically formulated are on a lattice, where different types of degrees of freedom live on links and vertices of the lattice. So you have gauge fields, these are white dots, let's say, that live on the links. And for this example, they will be the simplest degrees of freedom you can think of, that are just qubits, two-level systems on the links. And then they interact with matter degrees of freedom that sit on the vertices, and typically these are fermionic, and here the simplest example would be they are spinless fermions. Okay? And then every Hamiltonian LS gauge theory that involves both dynamical gauge fields and fermionic matter usually it's described in terms of 4 contributions that we classify as electric, magnetic interaction, and mass terms if you want. So generically, the electric energy term is something that acts locally on the qubits, in this case, of the single gauge field. So that's kind of simple. It's a simple single body operator. And then the problems start already when you start thinking about these so-called magnetic interactions. Because these are operators similar, actually literally like in the toric code in this case, that involve products of 4 operators of 4 gauge fields around an elementary plaquette. Okay, so that's already kind of the non-standard model to a certain degree. Then to make these 2 sectors of gauge fields and matter fields interact, we have this extra term which describes the hopping of the spinless fermions from one side X to its neighbor Y. But it does so depending on what the gauge field is doing in between. Okay, so that's also a bit of a funny construction, but that's generically how it looks like. And then finally, there's also a pure matter term that in this case looks like staggered chemical potential, but you can think of it as a mass to the fermions. So you might wonder why the hell does the theory look like this? Well, the reason is that we insist on a local set of conservation laws. And that's actually the defining characteristic of any gauge theory. So in this case, there's an extra operator, in this case it takes this form, which involves both the matter degree of freedom on a single vertex, and then all neighboring gauge degrees of freedom that go in there. And you can convince yourself that actually every term in this Hamiltonian commutes with this operator. Okay, so we have a massive set of symmetries, one for each vertex, which of course makes this Hamiltonian hugely block diagonal, but if you would diagonalize it, the thing would, the filter space would become extremely non-local, difficult to describe in a certain sense. Okay, so that's the defining characteristic of any gauge theory, and I call this here a Z2 gauge theory because this operator actually creates a local Z2 symmetry, so you can convince yourself that it's true. Okay, so that's kind of the basic structure of what a gauge theory looks like in general. Now, I was talking about QCD in the first slide. What does it take to quantum simulate QCD? In a nutshell, it's just upgrade all of this to the right symmetry group. And the right symmetry group is not this simple abelian Z2 group, but it's a continuous Lie group. In this case, in the case of QCD, as relevant for the real world, apart from going to 3 dimensions, obviously. We upgrade this group to SU3. And that's about all I would say here, because it takes quite a while just to write everything down. But believe me that basically, except for this technical overhead, the structure is more or less the same. So what does it take to simulate these theories? Well, first we should find, or in the spirit of hardware efficiency, it would be nice to find a hardware that actually natively can represent these kind of degrees of freedom. And I think now you already get the idea. There's gauge fields, which are kind of qubit-like, and then there's matter fields, which are fermions, essentially. And this needs to be upgraded just up to this technical difficulty to deal with the more complicated non-abelian groups. So the gluons are described by non-abelian gauge fields, which in the end should be represented by degrees of freedom that are associated with this group. Think of many qubits or a single large qubit. And the fermions, the matter fields, so the quarks, if you want, they're still described by fermionic matter degrees of freedom, but there's not just one of them for every set, but there's also many of them. Okay, so you need multi-component fermions. So that's already gives you an idea, what I'm going to do in the rest of the talk. Sorry, I should say also what's my goal. So the goal is to do something non-trivial, and just as an example, let's focus on real-time evolution using Trotter decompositions. So the goal is to implement real-time evolution corresponding to all these different for terms, but not specifically for this theory, but for theories of this kind. Basically, I would like to be able to do this for any theory that comes out of construction with a given gauge group. Okay, and I'll choose my favorite platforms for this, which are neutral atoms, and we've already heard quite a bit in the last week about the different platforms there are. I want to point out two examples that are very most relevant for this talk. So we've seen some discussion about fermionic atoms and optical lattices and how they naturally realize Fermi-Hubbard type models. So this is quite amazing to me. And they have been used mostly in an analog fashion so far, but we can of course also use the technology to do some more digital operations. And then we have heard actually much also about Rydberg atoms and tweezer arrays, which are used not only for analog quantum simulation, but also for these amazing digital developments where we move atoms around. We make heavy use of this Rydberg blockade effect to build entanglement gates. So this is just to say that the degrees of freedom I was talking about, namely fermionic matter, like in Fermi-Hubbard type systems, as well as internal levels, here in the case of qubits, but think of multi-level atoms to get qubits, are actually naturally available in neutral atoms. And they're in a sense perfect because they're given by nature, no? Like there's fermionic statistics, for example, is realized not by some crazy enigma mapping, but just because I actually work with fermions. Okay, so that's if you don't get anything else from the talk, that's the upshot. And then we have seen that there's these nice ways of building high fidelity entanglement gates, and I will guide you through now the type of gates that we believe would be nice to have in a more general architecture, and I give you a blueprint of roughly what we think it takes to simulate general molecular lattice theories coupled to dynamical fermions. Okay, so this is part number one of the story, and it's a paper we put out published last year, and this is concerned only with the gauge field part of the story. Okay, so forget everything I've said about matter. Let's focus on pure gauge fields. And remember, there were this electric term and the magnetic term, and the task is basically to deal with both of them. So first of all, I already said that basically, I want to use qubits to represent the gauge fields. And to be specific, let's take a finite but arbitrary group, so group G with D elements. And the Hilbert space of the gauge field, as said, is spanned by product can be spanned by computational basis, where I have one qubit for every link. Well, this can take D different levels depending for different elements of the group, but that's kind of the state of the gauge field I'm representing. And then, well, I said it, in principle, we can just encode this information not into multiple qubits, but just into a single qubit. So think of some hyperfine levels of some atoms, and store the information of the gauge field within internal state of the atoms. Okay, then there's this first term, which is an electric energy term, and without telling you again how exactly it looks like, remember from the first from 2 slides before, that this was an operator that acted on a single link. Okay, so this turns out to be true generally. So for arbitrary gauge theories, this is just a single qubit operation. So that's something that's relatively simple. The only thing you need to figure out is how to basically do arbitrary SUV rotations within this single atom. And if you ask your AMO friends, that's almost trivial. Every experimentalist knows how to address these levels. For example, by coupling with lasers to some excited state, you can do arbitrary rotations. So let's check that off, and I'll talk more about it. The challenging part comes with the packet interactions. Okay, so this is the magnetic piece of the Hamiltonian that I was talking about. And again, using the fact that we're dealing with a gauge theory means we have some underlying group structure, and this strongly constrains the structure of the packet operator, actually. And here I've written it explicitly in this computational basis for an operator that involves 4 links, 1, 2, 3, 4. And it turns out that this operator in this basis is always diagonal, and it's not a completely arbitrary function, but it turns out it's a function of a single variable rather than 4 variables. and what actually enters is the character of the, of that group element. For those who know some group theory. So that's a specified function that's given by the group structure, and it involves this product of G1 times G2 times G3 equals G4 inverse and so forth. So that suggests a very efficient way to decompose this operator that's given by this circuit. Okay, so what I have in this circuit is this special gate, that's this orange box controlled by this green ball, and that's what we call a group multiplication gate. So that's kind of a generalization of a C-naught, if you want. So it's acting on two qubits, and it changes the state of the target qubit by group multiplication with the state that the control qubit is in. Okay, and then if you convince yourself that what you need to do is just write the information of this product into the first qubit. So you do one entangling, another entangling, another entangling, and then the first qubit is in the state G1, G1, G2, G3 inverse, and so forth. And then this becomes a single qubit gate. So it's kind of the same strategy you would use, for example, to measure the Plaquette's inventory code when you do error correction, for example. It's the exact same story. And the nice thing is it's completely generic. It works for every group, because it heavily uses these group properties. And you can further decompose it into operators that just control a single control state, because this green thing really acts on, does something else for every of the states. Okay. So this is nice, because in this way we reduce this complicated operator this complicated four-body operator into a sequence of two-body operations, basically. And it also tells us what kind of two-qubit entanglement gates we need. Specifically, I would like to have a gate set that includes controlled unitaries for arbitrarily controlled unitaries, basically. Okay, and since I don't have too much time, I will skip how exactly we do this. The basic idea is that we leverage this idea of the Rydberg blockade. So by extending this level scheme to include also Rydberg state, I can play basically the same game that was used to build entanglement gates for qubits with Rydbergs, and selectively bring single control states, so to say, to the Rydberg level, and then on a nearby atom, nearby target qubit, so to say, I do an operation that passes through the Rydberg state and thereby creates this selective control, and actually allows me to do this kind of gates. Okay, so that's a quick overview of the gate field part of the story. And now we would like to upgrade this to include the fermionic operations as well. Okay, and so what does it take for this? So the reference for this is nicely summarized in a recent paper. So what we need on top of the qubits for every link is we now need also fermionic modes that represent these quarks, let's say. And as I told you, there's one fermionic mode for every vertex in this lattice structure, but there can be multiple ones of these, and I just keep track of them as an additional label alpha. And to be specific, I show you one example that we have in mind, but there's other technical structures possible. So the basic idea is again to use fermionic atoms and to encode this multiple fermionic states in actual fermionic, in hyperfine sets of actual fermionic atoms. So neglect all of these level scheme and just look at the first one here. So strontium actually works, any alkaline earth atom works equally well. You have large ground state manifolds that you could use as actual fermionic atoms with different levels. So think of basically a multi-species just within one atom. That's one way to think about it. Okay, so the trick now is that if you use an architecture like this, then you can use the same atom to represent both either qubits or fermionic atoms. And the difference is only whether they're fixed on a link, so they're trapped on a fixed tweezer, or they're allowed to be delocalized over different lattice heights that are the vertices of my lattice. And then if I have a level scheme like this, for example, here I have some excited states, so I can play my internal qubit games to do arbitrary qubit rotations. And this already takes care about the third term, or the fourth one actually, that I showed on the second slide. So this single, these operations that act only on vertices, that are kind of the mass terms for the fermions, they now take the form of single qubit gates, and I have taken care of basically already. So the next thing, and that's kind of now where the tricky part comes, is I need to couple these fermionic degrees of freedom to the qubit type degrees of freedom. And in general, the interaction looks something like this. So I have a fermion qubit type interaction, where I have a multi-level fermionic atom hopping from a site from two sides, x to x prime, and potentially change also its internal state, so different alpha and beta. And in between, I have a matrix of operators that tells me what the gauge field is supposed to be doing. So that's a bit nasty, but it turns out that once again, the structure of this term is very much restricted by the group properties, by this fact that we're interested in the gauge theory. And it turns out that there's a circuit that simplifies this already. And here I have the same kind of group multiplication game basically I had before. Now not acting between two different qubits, but acting entangling a qubit with what I treat as a fermion. Okay, it's not actually, it doesn't feel that it's a fermion at this point because it doesn't hop around. No, it's just actually entangling them. Okay, I should be a bit quicker maybe. Okay, so the trick is that this operator U that appears here is basically the same operator that enters into the plaquetron, and this is why this operation can be disentangled, but first entangling the qubit of the fermion with the qubit of the gauge field, and what remains here in the middle is an actual direct tunneling process. So something where this U matrix is just a delta and alpha and beta. Okay, so I haven't solved the problem yet, but I've broken it down to now the additional requirement that I need to implement ordinary tunneling in a digital fashion. And luckily we've been working on that as well. So we discussed one technique that we call the shuffle gate. We didn't really invent the wheel here, but we used nice properties that were known about alkaline earth atoms. So the idea roughly is something like this. So the trick is that for alkaline earth atoms, you can use independent trapping potentials for the ground state manifold as well as its excited state. So this allows you to play a game where I treat this level as kind of storage, so they are fixed in place. This is where my atoms are supposed to be going and tumbling around. And the second optical trap I kind of use as a shuttle. Okay, and then I can run a protocol like this. If I want to do a tunneling between two tweezers, let's say, and just bring one transport tweezer over to a pipe pulse, so that's an internal rotation. So I switch both the internal level as well as the trap I'm in. Then I physically move the tweezer around, as has been demonstrated recently, for example, Misha's group. Then I do another rotation, an internal rotation that creates a desired superposition, and then afterwards I clean up by bringing it back. And you can convince yourself that in the language of fermions, this directly implements a tunneling event. Okay? So that summarizes basically everything. Okay? So if we had a fermion qubit architecture made out of these atoms, in principle we're able to realize every single term, every arbitrary gauge theory of finite groups. Okay, that concludes the hardware part, and I'll spend the last couple of minutes on a more software development, because I've swept one detail under the rug, and that's the fact that I've been focusing on finite groups. And that's kind of a technical, it looks like a technicality, but it's actually a problem if you want to make this more seriously quantitative. And the reason is that this subgroup, you can think of this as a truncation. If I'm actually interested in SUN, I can pick a subgroup which kind of is a truncation of my theory. But this truncation is ultimately uncontrolled. So either you know this as a math fact, or you can think of SU2 as a sphere and try to put a regular polyhedron inside. That you realize you cannot do this arbitrarily fine. So there's a proposed way around, which is kind of a dual picture. So instead of working in this group basis that I've been talking about so far, you can work in the dual basis that's kind of the Fourier transform of that. If you don't know how this works for non-abelian groups, here's an example of FC2 I guess everybody's familiar with. So these levels J and N then correspond to J and quantum numbers like here. So the J just labels irreducible representations of SU2, and the M and N are kind of two couples of magnetic quantum numbers as spins. And the obvious choice here is just to kind of restrict the Fourier modes, to say I take all J's up to cutoff K. Okay, so that sounds like a good idea. Sounds more controlled. I can just increase this cutoff. Unfortunately, every decomposition I've showed you in the previous slides breaks down. Then. Okay. That's sad, and it has to do with the fact that I was using this group multiplication. Games. So we were looking for something else, and proposed this recently. And that's kind of a fun story. Unfortunately, I'm running out of time, so I'm going to be quick. But if you're interested, I invite you to have a look at the paper and ask me later. So the idea is to deform the actual symmetry group, technically deforming the algebra to a Hopf algebra, or sometimes called Q deformation or quantum group. So either you know what this means, or if, then you might be interested to hear that it's important to choose this deformation parameter as a root of unity because this leads to the right irreducible representations. If not, just believe me that this comes with a host of nice mathematical properties, algebraic properties that we can use to exploit to find new decompositions again. So one thing that happens, for example, is that you can write down nice Gauge-invariant bases for our qubits. For example, for a 2D square lattice, it's convenient to go into a basis represented by graphs, by trivalent graphs, where qubits live on every links, and at every trivalent vertex, something like a fusion constraint. The Plaquette operator becomes a bit more complicated. For people familiar with string net models, it's actually pretty much the same. So we get a Plaquette operator that acts on these qubit degrees of freedoms and is controlled on all the external ones. So that looks a bit messy, but we actually figured out a quantum circuit that diagonalizes this exactly for arbitrary truncations, and thereby kind of recovers the properties we had by this analytic decompositions for arbitrary groups that we had before. Again, I'm being very quick here. But for the experts, the trick is to use the fundamental non-uniqueness of the spin network basis of solving this Gauss's law and performing local unitary transformations that are these controlled operations on a single qubit controlled by 4 octagons that kind of changes locally the basis and allows us to diagonalize the Plaquette operation more or less analytically. And if this looks very crazy, let me just summarize by saying all of this is realizable with the exact same data set I was saying before in a somewhat, at least formally efficient way. So there's polynomial decompositions of all of these nasty operations, such that this hardware I was talking about remains applicable. Okay, so with this, let me come to the end. I've showed you somewhat of a quick, high-level overview of the fermion qubit type architecture that we have in mind, that in principle would allow us to simulate arbitrary lattice gauge theories. And just to summarize, the important feature here is to use atoms with the right properties. First of all, they need to be fermionic. Then they need sufficiently many internal levels. And then we need to play some other tricks to realize these tunneling gates, for example. So for that, it's actually quite useful to use alkaline earth type atoms. And just for you to remember, if you actually want to do this, you need to have a sufficiently reconfigurable trapping potential or Rydberg array, such that you can fix some of the atoms on links for which you will only use the internal states. So you treat them as qubits, and they will play the role of the gauge field. And then for the other ones that sit on the vertices, you need to be able to delocalize them, and they will play the role of fermionic matter. So we haven't really talked about applications. Really, one thing that we tried or played a bit with is, for example, wave operational algorithms, if you like that. But then the other story I briefly touched upon is that there's still work to do on the theory side, how to truncate these theories and how to put them into manifestly finite dimensional Lilith spaces. And this idea, what we call SNAC, spin network algorithms for uniform lattice gauge theories, I like very much, and I think it's a good idea to go forward. So the question we are going to ask on the theory side is actually now, does this help us to approach the continuum limit of these theories? Because in the real world, we're talking about field theories, and today I've exclusively talked about their lattice formulation, so there's an important step missing to actually do high-energy physics. And in this context, it's important to study certain phase transitions in these models, and that's actually also kind of interesting from a condensmatter perspective, because there are deconfining transitions and there's topological order in there. And we started playing with some tensor network ideas compared to Monte Carlo later, and it looks kind of promising. So if you're interested, I'm happy to talk more about that as well. So with this, let me wrap up. Here's a list of references, all things I've been touching upon. There was a bunch of people involved in this, especially in these fermionic architectures. And otherwise, I want to highlight in particular another postdoc from our group in Innsbruck, which is Daniel, and of course, Peter Soller was essential in this work. And I would like to thank you for your attention.
So, questions? Yeah, so regarding error correction, so how do you, if you wanted to move towards error correction, and you have these fermion degrees of freedom, is there any natural encoding that would preserve that? And how do you sort of move towards fault tolerance?
Short answer, I don't know. And the bottleneck is the fermions. Yeah. Longer answer, I think for qubits, it's kind of straightforward to kind of extend all of this. For fermions, as far as I know, there's not so, or at least I'm not aware of a single code that actually encodes fermionic modes into a single logical fermionic mode into multiple fermionic modes, and I think that's, well, somebody needs to come up with an idea how to do that.
Or prove it doesn't exist, yes.
Good point, yeah.
Good.
Yeah, easier question. So you mentioned to put fermions into research, but then you do need to accommodate hopping terms. How would that go?
So I need to what?
Accommodate hopping terms.
Yeah.
So that was out with research.
Yeah. So one way was this thing I was sketching quickly, is that you can use. Okay, so there's actually multiple options. So the first one, which is maybe naive, but in principle works, is you physically move two tweezers together, let them merge, become a double well, physically tunnel, and then move them apart. So that has been demonstrated, but the fidelity is kind of not so good, and it's also like experimentally very challenging. Another thing that might be easier to scale, but again, I'm not an experimentalist, is this scheme of what we call a shuttle. So where you use a second kind of transport trap that you physically move around. This could also be optical lattice, for example, so it's more stable. And then you can do internal rotations, move an atom over, do a superposition, and then move the storage back, and then undo the initial pipe holes. And if you do the math, you see that this is equivalent to a tunneling. So it's kind of a digital way to realize tunneling by internal rotations plus actually moving. So that's also the whole story is extremely challenging, I would say, from an experimental point of view, because the point of using fermions is to stay with the fermionic statistics. So during all of these operations, I have to remain in the same motional state, right? So at the moment I have a bit of heating or something, this will introduce errors.
Okay, thanks.
Can you explain a bit more about this Q-deformed quantum group? Is it a subgroup, and how does it approximate the V group in some sense?
Yes, it's okay. 1 second. Yeah, so here's a simple example. So what you actually do is you deform the algebra. So it's not a subgroup. It's also not a Lie group anymore. Technically, it's a Hopf algebra. So what you do is, what needs to be done can be illustrated for the case of the bosonic oscillator. And the trick is that you want to keep the ladder operators the same, and you just deform the commutation relations of the of these two guys. Okay, so you can write down what's called a Q-deformed algebra for the harmonic oscillators that look like this. Okay, so that's technically what you do. And the trick is that this naturally, if you think about representations of this algebra, that you can naturally represent this on a finite dimensional Hilbert space, where the operators basically look like the same. But what you need to do is you need to replace ordinary numbers with so-called Q numbers, so that behave a bit funny. And then you can convince yourself that this is the algebra that works. So what you do for SU2 is then kind of, for example, you can use stringer bosons and use these Q-deformed oscillators that I showed you very briefly to define spin operators in terms of these Q-deformed bosons, which are not really spin operators, but this is the algebra that you have. So this makes sure that the commutation, that the raising and lowering properties remain exactly the same. And this is weird, But what you see here also is that if you send now Q to 1, then this reduces to the ordinary algebra. So you're guaranteed to converge in that formal sense. And this happens if K goes to infinity, because then the root unity goes closer to 1. So in that sense, that's a controlled truncation. And then there's a bit of heavy lifting to understand the representation theory of this. So here's a paper where it's worked out in detail from the beginning of the 90s. So people care about this in somewhat different context. And then you can show that there's a bunch of representations that have nice properties that we can use to build a closed fusion ring, and that's what ultimately is necessary to write on these gauge invariant bases on which we construct the from. So I'm happy to chat about details, but maybe offline.
sync Torsten.